Imagine needing exact amounts of water or gold to fill a container. These materials divide down to the milliliter or milligram. You can pack your container until no space remains. Because we can fill every unit of capacity, our total profit depends on the value of every individual unit of weight we pack. This means we have to find a way to measure which items give us the most value for the space they occupy. This table shows our problem. Item A weighs 10, profit 60. Item B weighs 20, profit 100. Item C weighs 30, profit 120. We must pack these items into a knapsack with a strict maximum capacity of 50. Our goal now is to process this exact dataset step by step, mimicking the strict sequence of logic a computer algorithm uses to solve for the best possible result. To figure out which item is the most valuable per unit, we calculate the profit-to-weight ratio. By dividing the profit by the weight for each row, we see item A yields 6 per unit, B yields 5, and C yields 4. Next, the computer sorts the entire list based on these new ratios, placing the highest value at the top. In this case, the order aligns: A, then B, then C. A common error in exams is sorting by raw profit, raw weight, or sorting in ascending order. To stay greedy for the best value, you must always sort by the descending ratio. Organizing the data this way ensures that when we start packing the bag, our very first choice yields the highest possible return for the space it occupies. We start at the top of our sorted list. We take all of item A. It weighs 10, dropping our remaining capacity to 40, and it adds 60 to our total profit. Moving down the list to item B, we have plenty of room. We pack the entire item. Our capacity drops by 20, leaving us with 20, and our total profit reaches 160. Now we hit a physical limit. We reach item C, which weighs 30, but our bag only has 20 units of space left. A whole item C cannot fit. This is where the divisibility rule kicks in. Calculate the exact fraction of item C we need to fill the bag, and determine what that fraction does to our profit. We need 20 units of space out of the 30 units item C weighs. That simplifies to a fraction of 2/3. To find our added value, we multiply that 2/3 fraction by item C's total profit of 120, giving us 80. We pack that final fractional piece. Our bag's capacity zeroes out, and our total profit settles at 240. Slicing the final item allows us to use every unit of the bag's capacity. This ensures we maximize the profit within the strict weight limit provided. Let's analyze how fast this algorithm runs. Calculating the ratios takes O of n time, sorting the items takes O of n log n, and traversing the list to pack the bag takes another O of n. Out of these 3 steps, sorting the list requires the most work. If you have 1,000 items, walking through them is quick, but arranging them in descending order takes more time. Because the sorting step takes significantly longer than any other task, O of n log n becomes the defining overall time complexity for the algorithm. This comparison proves our approach. Bag 1 shows a suboptimal choice with a lower ratio item. Bag 2 uses our greedy algorithm, taking the highest ratio item first. Swapping one lower ratio unit in bag 1 for a higher ratio unit keeps weight identical but increases total value. This logic, known as the exchange argument, demonstrates that replacing a lower performing unit with a higher performing one will always raise the total profit. This proves that prioritizing the highest profit-to-weight ratio is the mathematically optimal path. To lock this workflow into memory, remember this sequence. Calculate the ratio, sort in descending order, take the whole item if it fits, take a fraction if needed, and calculate the profit. Following these 5 steps consistently ensures that you reach the correct mathematical solution every time you solve a fractional knapsack problem.